So as a sort of starting point for talking about rotation, I think it's worth actually doing a little bit of remembering where we've been so far. So what's the big picture thus far, and how does that big picture line up with respect to where we're going? So thus far in this class, we've really been talking about how do we model particle motion. And when we talk about modeling particle motion, in some ways we've introduced two kind of frameworks for this. One framework is a continuous framework, and the other framework is a sort of before and after framework. So, and we've probably spent more time on the continuous framework, on the before and after framework, but to sort of remind you of what the big ideas are in this continuous framework, the continuous framework is one where you basically ask the question, what's the system? That is, what are the system boundaries for this? Once you've identified the system boundaries, you figure out what are the interactions and what's the free body diagram. You choose a coordinate system. So this is where a lot of the work that we did in the first module, like for example in working with polar or working with natural coordinates, comes into play. And then finally, using that coordinate system and using those interactions and mathematical models for those interactions and using that free body diagram, you finally are able to come up with a governing equation that describes the time evolution of the system. You come up with a differential equation, and the differential equation for modeling particle motion really always boils down to saying that the sum of the forces on the system tells you what the time rate of change of the momentum of the system is. And of course, one of the things that we spent a fair amount of time in the last module on was really thinking carefully about this time rate of change of momentum in the system, and thinking particularly about momentum flows that might not just be due to forces, but also due to masses crossing the system boundary. Now, we also have done a little bit of sort of thinking about a before and after framing, where instead of thinking about what happens continuously in time, we're actually interested in what the system is doing at each instant. We actually think about some event and we ask questions about what was the state of the system before the event and what was the state of the system after the event. And so for this, we've really been using a sort of momentum conservation framing, which is to say that the momentum before the event and the momentum after the event have to be equal to each other unless there's some other sort of change in momentum that happens to the system. Unless you've got something added, something that happens during that event that either increases or decreases the momentum of the system. So the initial momentum is the final momentum, and actually the final momentum is the initial momentum plus whatever change in momentum there might have been during the event. So this is the way that we often deal with things like, for example, very short time range interactions. So this is where the idea of impulse comes into play. And it's often useful when you've got a system where you don't know details of the forces, but you do know something about what the sort of conservation properties of the system are. Okay, so that's sort of what we've been up to thus far in the class. And I'll note that, really in the first module, we were asking questions about this, and then the second module was sort of taking that information about coordinate system and also about the sort of kinematics in coordinate systems and extending it to this idea of momentum conservation, extending this idea to the idea that forces are a flow of momentum. Okay, so where we're going with this now is actually trying to expand from a particle model of the world to a rigid body model of the world. So instead of talking about things just as being point masses that are located at the center of mass of the system, we instead start to think about things as actually objects that can not only translate but rotate. So and I will note that there's an important distinction here. We've now introduced the idea that an object can rotate. Back in this framing that we used earlier is one that is purely a translation framing, right? That is, we're interested in how things move around, but not in them actually rotating. So for example, when you did the diagnostic with the rocket, you're interested in the translation of the rocket. You actually don't ask questions about whether the rocket is stable in that diagnostic. You don't ask questions about how the rocket might rotate in space. You just assume that that rocket is a point mass that's always lined up in the direction of the velocity. Well, in order to deal with how objects translate and rotate, we're actually going to use an approach that's very similar to this one. We're going to think about both a sort of continuous model and a sort of before and after model. And we'll actually follow some very similar steps here. So we're going to again be thinking about what are our system boundaries, what's the free body diagram, what's the coordinate system, and so on. But when we actually come to figuring out what the equations of motion are, right, we're going to have to come up with some differential equations here. Those differential equations somehow have to express not only the conservation law that has to do with translation, which is this conservation law, that is that momentum is, that force is the flow of momentum, but also a conservation law that has to do with rotation. So the differential equations that we end up with when we start to talk about rigid body motion are not only that the sum of forces tells you the time rate of change of the linear momentum, but also that the sum of torques tells you the time rate of change of what's called the angular momentum. So in some ways, we're actually doing very much the same thing in the continuous space that we've already done. It's just we're extending it to think about not only forces, but also torques. And so we actually have a lot more equations to deal with. It makes sense that we have more equations to deal with because we've actually got more complicated motion to deal with. We have to deal with both translation and with rotation. And in some sense, you can think about these two equations as being sort of the translation equation and the rotation equation, although I will caution you that there's a little bit of danger in doing that. Similarly, there's actually a very similar sort of framing in the before and after space. In the before and after space, we now start to think about not only that the final momentum after some event is equal to the initial momentum after some event plus whatever the change in momentum is, but also that the final angular momentum is equal to the initial angular momentum plus whatever the change in angular momentum is. So there's very much this analogous idea at the high level between how we deal with rotation and translation of rigid bodies and how we deal with particle motion. So that's the high-level framing of where we're going, and how where we're going ties to where we've been. There's also a lower-level framing of that, which is to say that when we talk about where we've been talking about translation. One of the things that we are really translating to now, or moving to now, is talking about rotation. And just as there's sort of a high-level analogy between the way we talk about particle motion and the way we talk about rigid body motion, there's also a high-level analogy between how you talk about translation and how you talk about rotation. For example, in translation, you talk about velocity and you talk about acceleration, you talk about momentum, you talk about forces, and you talk about mass. And in rotation, there are actually very analogous kinds of quantities that it makes sense to talk about. In rotation, you talk about angular velocity, which is a vector, right? It's sort of analogous to linear velocity. You talk about angular momentum, denoted alpha, which is a vector. You talk about angular acceleration, alpha, which is a vector. You talk about angular momentum, a vector. You talk about torque, a vector. And you also talk about moment of inertia. And moment of inertia, I'll note, is a scalar when you're talking about two-dimensional rotation, which is what we'll be talking about in this class. As you move into three-dimensional rotation, which I'll mention briefly in some of the videos, this analogy becomes a lot more complicated. So I'll put a little warning sign here. And just to remind you of what these things are, this omega is angular velocity. Units are radians per second. Alpha is angular acceleration. Units of radians per second squared. Angular momentum is denoted by L. And that's actually kilograms meters squared per second, or what the units are of that. Torque is denoted as tau as a vector. Units of that are Newton meters. And moment of inertia has units of kilograms meters squared. So just as in talking about the big level, there are analogies. There are analogies at the lower level as well, and these analogies extend not only to what the quantities are, but also to what the governing equations are. So in some sense, for example, just as the acceleration is the derivative of the linear velocity. Angular acceleration is the derivative of the angular velocity with respect to time, just as momentum is mass times velocity. Angular momentum is moment of inertia times angular velocity, so long as we're in the two-dimensional condition here. And just as force tells you what the time rate of change of angular momentum is, torque tells you what the time rate of change, just as force tells you what the time rate of change of linear momentum is, force tells you what the time rate of change of angular momentum is. So there are a lot of analogies to be made between translation and rotation. And one of the things I encourage you to do as you work on rotation is, if you get confused at some point, take a step back and ask the question, what's the linear translation version of the equation? And then does that help me think about what might be true for the rotational case?